Hello everyone, my name is Bhiman. I'm a PhD student in computer science at the University of Pittsburgh. Welcome to the third and final part of our deep dive into DeepSeek-R1 series, where we are uncovering how DeepSeek-R1 managed to beat OpenAI in reasoning. If you haven't watched the first two parts yet, I highly recommend doing so before continuing. Their links are in the description. That being said, let's begin the final part of this series. Previously, we explored how DeepSeek R10, unlike conventional LLMs, uses GRPO instead of PPO in its RL stage. We discussed that the main motivation behind this innovation was to reduce training costs. We were then left with a key question: how did the reasoning ability in DeepSeek R10 actually emerge? To find the answer, I ended my last video with two questions. What is the difference between the query of DeepSeek R10 to that of conventional LLMs? And what is the difference between their reward models? In conventional LLMs, query usually contains a mix of diverse tasks. In contrast, DeepSeek R10's queries are made up of maths, coding, and similar objective tasks. You might ask, maths and coding are two different subjects. So what's similar here? I will come back to categorize their similarities in a moment. But first, we need to understand the reward model differences. If you remember my first video, the reward model in conventional LLMs is trained using human preferences. Collecting these preferences is expensive, and more importantly, it limits learning to what humans prefer. This means if human preferences are biased, the model would likely mimic those biases. DeepSeek takes a different approach. Instead of human feedback, the team uses a rule verifier as the reward model. Both types of reward model give a score for correctness. However, rule verifiers are cheaper, easier to implement, and free from human bias because they rely on objective rules. The catch is that this approach only works for tasks with objective answers. And what kind of tasks are those? Exactly, maths, coding, and similar problems. For example, in coding tasks, you can run test cases and check how many pass. For puzzles, there's usually a single correct solution. On the other hand, subjective tasks like rating the quality of a poem are difficult for rule verifiers, but human preference models can handle them. These restrictions to objective tasks might sound limiting, but it's actually not a major problem for developing reasoning abilities. Why? Because reasoning in LLMs is mostly evaluated on maths, coding, and puzzles, as these domains require deep reasoning even for humans. So, if an LLM can solve this, it's a strong indicator for reasoning ability. But what does even reasoning look like in a language model? What characteristics must a model show to be considered capable of reasoning? Let's start with humans. When a human is asked a question, we think through a sequence of steps before giving an answer. Now compare this with LLMs. Regular LLMs usually output the final answer directly. In contrast, a reasoning LLM behaves more like a human. It first generates a thought process and then provides the final answer conditioned on that reasoning. However, this thought process must make sense. If it's just gibberish, it doesn't count as reasoning, even if the final answer happens to be correct. For the thought process to make sense, it should follow a logical structure, typically a sequence of clear steps leading to a solution. Humans do this naturally, and we want reasoning LLMs to do the same. As you can see from the example on the screen, the information from the math problem is broken down into logical steps to arrive at the final answer. Technically, this structured thought process is called chain of thoughts. You may have heard of chain of thought prompting, which have been shown to improve reasoning in regular LLMs by explicitly asking them to generate a thought process before answering. DeepSeek R10, however, learns this behavior through reinforcement learning rather than prompting. Remarkably, by using extremely simple prompts and rewards in its RL pipeline, DeepSeek R10 was even able to surpass every existing reasoning model, including OpenAI's then state-of-the-art model O1. So, let's take a look into these simple prompts and rewards. This diagram shows the overall setup. The query uses a simple prompt and the reward model applies straightforward checks to train the policy model. Let's start with the query. It consists of two parts, a system prompt and a user prompt. The system prompt is what I'm calling the simple prompt. It asks the model to do just two things: place the reasoning process inside think tags and place the final answer inside answer tags. On the right, you can see an illustrative example, and on the left is the actual prompt. It's simple, no fancy instructions, just clear formatting rules. The user prompt is the actual question, such as a lead code problem. Together, these make up the query given to the policy model. The policy model then generates the reasoning chain and the final answer as shown on the right. Finally, the reward model performs three deterministic checks. Does the output use the think tag? Does it use the answer tag? Is the final answer correct? Example, does the code compile and pass test cases? These rewards are easily computable, requires no human involvement, and provide no explicit supervision on how to solve the problem. The model must figure out the reasoning strategy on its own during training. These rewards are then used to train the policy model using GRPO, which I explained in the previous video. Link is in the description. This simplicity in the query and the reward model encourages implicit learning, which led to the emergence of DeepSeek-R1 Zero's impressive reasoning abilities. As shown in the left plot, during training, the model learned that thinking for longer improves accuracy. The right plot shows that with more thinking steps, DeepSeek-R1 Zero solved more maths problem correctly. Another fascinating phenomena emerged during training: self-reflection. The model learned to identify midway when its current steps were wrong and to switch strategies to reach the correct solution. The authors call this the aha moment. Interestingly, this self-reflection was not planned or explicitly trained. It emerged naturally from the setup. Together, these elements led to the emergence of DeepSeek-R1 Zero's reasoning abilities. However, there was a major challenge. DeepSeek-R1 Zero wasn't fluent and it often mixed English and Chinese in its answers. To fix this, the authors introduced 3 tweaks to the training recipe, which gave birth to DeepSeek-R1, the model that made global headlines. Let's uncover these tweaks one by one. The first tweak was to introduce supervised fine-tuning step using only 1000 long chain of thought examples, a tiny number compared to Llama 3. This step primarily aimed to teach fluency. Next, they introduced a new reward in the GRPO stage that explicitly checked whether the output was generated in a single language. Finally, they reinforced fluency and consistency through an additional SFT stage, this time with many more examples, combining reasoning and non-reasoning tasks. This was followed by one last round of GRPO training. Even with these extra steps, the overall recipe was still much lighter than conventional pipelines like Llamas, which repeats SFT and RL 6 times. These 3 tweaks, combined with the original efficient setup, resulted in DeepSeek-R1, which outperformed OpenAI's O1 on reasoning benchmarks, all at a fraction of the cost. It was smart, efficient, and innovative training strategy that made headlines worldwide. Here are the references to the papers I used throughout this 3-part deep dive into DeepSeek-R1. I hope you learned something new. Thank you so much for your time, and I will see you in the next one.